Section 2.5 deals with implicit differentiation. So far, we've only taken the derivative of explicit functions. Explicit functions are equations where one variable is already by itself or solved for. So far, we've looked at things that are y equals, f of x equals, g of x equals, h of x equals. We've never really looked at anything where the variables are mixed up. So today we want to look at differentiation when the function's equation is implicit, meaning the variables are mixed up and the dependent variable isn't solved for. In order to understand implicit differentiation and how it's different, I want to talk to you about y equals 3x squared plus 2x plus 1. That is an explicit function. One variable is already solved for by itself. But you need to understand that differentiation is a mathematical operation on two variables, not one. And it must be performed to both sides of a function. We don't just leave off the y and say that this equals 6x plus 2. We say that the derivative of y with respect to x is equal to 6x plus 2. Does that make sense? Okay, so we can't just say y equals 6x plus 2, and we can't just say that the whole thing equals 6x plus 2. We have to literally take the derivative of this side. What is the derivative of y with respect to x?
1.
Are you sure? That's the derivative of x with respect to x. What's the derivative of y? What do I usually put here when I take the derivative?
Y prime.
A y prime. The derivative of y is 1y prime. Do y'all understand that? You've done it. We've never made a big deal out of it, but I've told you notation is really important, right?
Right.
Okay, so the derivative of y is 1, but it's not with respect to x. It's not with respect to y, it's with respect to x. And that's why you see the 1y prime pop up when we take the derivative. Now, what's the derivative of 3x squared? 6x. With respect to what?
Y or x?
X. We're always, for now, we've always differentiated with respect to your independent variable, which has been the x's. That's why you don't see an x prime. So notice that when we take the derivative of the y, we see a y prime. Assume that spot. But we don't when we do the x's, because they are with respect to themselves. So you don't actually see the notation for the derivative, you just see the actual derivative. I know that may sound a little confusing, but once you see the difference, I think it'll make a little more sense. So for our first example, we're going to take a really basic function. We have 5y equals 3x plus 9, and we are going to differentiate with respect to x. In other words, that's me asking you to find y prime or dy dx. The only way it's worked differently is that the y isn't just a 1y. Now it's a 5y. Well, if that were a 5x, what would its derivative be? 5. But it's not a 5x, it's a 5y. And so it's really 5 times the derivative of y with respect to x. We say that's a y prime. So you take the derivative of a y the same way you would an x. But every time you take the derivative of a y, you have to put a y prime with it to indicate that it's a dy dx. Equals, what's the derivative of 3x? And technically that's 3 dx dx. But that cancels, so we don't have to show that. It doesn't get a prime. And then, what's the derivative of 9? 0. So we say we're done with the differentiation, and at the end you isolate the y prime, and then you're finished. So if I divide both sides by 5, I get y prime equals 3/5. I would have gotten the same thing had I isolated y to start with. So that's the derivative. Y prime equals 3/5. For our second example, we want to differentiate the following with respect to x. And for now, I'll leave it with respect to x, just so you can get your feet under you. But I could say with respect to anything. If I said with respect to y, the x's would get the primes, and the y's wouldn't. But for now, we'll stick with x's so that it doesn't confuse you. So if I'm going to take y squared equals 4x cubed, and I am going to take its derivative. The derivative of y squared is 2y, and that is the derivative of y with respect to x. So to indicate that, we put a 2y y prime, or, and your book does it this way, so I wanted to show you, They always do implicit differentiation by putting a dy dx instead of a y prime. Doesn't matter, they're equal. Now the 4x cubed has a derivative of 12x squared. And I don't have to put this is called a differential. I don't have to put differentials with it because I'm taking the derivative of x's with respect to themselves. So you don't show that because I'm going with respect to x. That's the one that doesn't get the differential out there beside it. This notation is the same as writing 2y, y prime. I prefer this because it doesn't look like it has a fraction in it. It doesn't matter. You can do it any way you want. So we're just going to put the y prime there. Then you just isolate the y prime by dividing both sides by
2y.
So we have y prime equals 12x squared divided by 2y, which is 6x squared over y. So that is the derivative with respect to x of the, this isn't actually even a function. This is a sideways parabola-ish, yeah? Well, actually, I have no idea what that shape is. It would be a really weird graph because the y's are squared, which tells me it's not a function. The x's are cubed, so it wouldn't be a parabola. We would have to actually look at it. Maybe we will if we have time. So that's the derivative with respect to x. What does that tell me? Does anybody have any idea what it means?
Something about slope?
It tells me something about the slope. If I could get a graph of this function, and I think you and I will in a second, we'll pause and we'll look at the graph of that, then I could take any x value and any y value on that graph, and I could substitute them into the derivative, and it would tell me the rate of change of the x values with respect to the y's. So let's say that the x's were distance or time, and the y's were distance. Then it would tell me the speed of whatever was moving along that trajectory is what it would tell me. So it does tell you the slope of the graph, but it just happens to involve x's and y's. Instead of normally we see slope only involves the x. Kind of sketchy, but starting to make a little bit of sense. Okay. Let's pause there and actually graph it.